Thanks, everyone, and good afternoon. Welcome to today's Space Syntax Lab seminar. We're delighted to have Dr. Chen with us to present his work on the multimodal spatial impacts of public transport networks on urban systems, with a focus on London and Taipei. Po holds a PhD in space syntax here from the Bartlett School of Architecture, UCL. He specializes in urban and transport research, exploring how railway and multimodal transport networks shape urban form and socioeconomic growth. And currently, he's a senior consultant at Space Syntax Limited, where he brings extensive experience in GIS, geodatabases, and integrated urban modeling. His work harnesses advanced spatial analyses to inform evidence-based urban planning and design, offering insights into the role of multimodal transport in promoting sustainable and integrated urban development. And before we begin, please note that if you have any questions, feel free to post them in the chat so we can address them at the very end of the seminar. And with this, I'd like to hand over to you, Paul.
Thank you so much. Yeah, thank you so much, Kimon. I just completed my PhD last December, and now I'm working full-time in space syntax. Just like Kimon mentioned, specialized in geospatial data sets development and the data analysis. Today, in the seminar, I'm going to partially present my work of PhD, which is about applying the multimodal network modeling into to assess the impact of the public transport network, and then use the case of London and Taipei and to identify those influences. The research starting from the question about how do we travel every day, and especially in this kind of metropolitan area, like big city like London, New York, Paris, Tokyo, which is heavily relying on public transport. And so here is an example showing that in 2023, almost 33% of the population commuted by public transport in London, and also 25% of the commuter is by walking. So this is the combination of the walking and the public transport is above, is almost 60% in London now. So this is the starting of the research questions and then research interest. In the urban form or urban morphology study, usually we're starting from looking at the blocks of a city or a region. And then moving forward, we would like to know those relationship between the blocks, between the region or cities. So we start looking at the street network. However, beyond the urban blocks and the street network, especially in the big cities, highly developed cities, which has relying on the rail network, this part of the infrastructure, or this part of the spatial relationship is usually ignored in most of the urban study. So that's why my interest is to look at what kind of impact or relationship when we considering also the rail network into the spatial analysis. Just like I said, like this image shows the Battersea, which is a newly developed area in London. Although we know there's a Battersea power station which is redeveloped into a high retail residential area, but we can see those railway infrastructures still occupy a lot of ground in the city, which is somehow ignored or is not taken into high attention in the urban morphology study. So yes, the research arm is to investigate how rail networks interact with the urban form, and further to look at how this rail network influence the land use patterns. By employing the network analysis and the spatial modeling to assessing this kind of spatial social development. And also the research asking is to what extent can our understanding of the urban form and function be enhanced by incorporating this railway network in this kind of metropolitan cities. Some of the literature relating to the rail transport network study, especially in the spectator field, is quite limited. So starting from some neighborhood scale study is mostly is looking at those spatial relationships next to the station in the neighborhood scale, and to see what kind of movement or what kind of impact to the local land use or activities, socio-economic activities. And then moving from the neighborhood scale, there's some of previous study focus on the city or regional scale. For example, Chaladia focus on how commuters behave above the ground and in underground, and how the differences between these two. And Swanda look at the network accessibility shift by looking at the railway network. Also, Venice and Stock, they focus on how the railway stations as a place to influence the urban functions. And lastly, there's also very limited literature in space syntax field about talking about the multimodal network, which is combining two different types of the transport network by combining the street network and the rail network to assessing this kind of spatial influence. So the methodology is to evaluate, in order to evaluate this kind of the impact of the railway networks. This research is aiming to create the multimodal network model, MNN, to develop and to integrate the railway network with the street network into a unified or a single model, and applying space syntax method and methodology to look at the different types of the graph distance measures, including angular, topological, and metric. Most important thing is to also incorporate the travel time distance into the spatial analysis. And the multi-network model is further integrated with other additional GIS dataset or census dataset, and to develop an integrated urban model, which allow us to assess the social or economic performance of the city. So here is a diagram to show what is the multimodal network model, MNN, and what is the IUM framework in this research. So on the first floor, from the top left is the road network, which we usually use in space impact. And then to combine with the railway network to create a multi-network model, it requires a link between these two layers. The link is through the station node to link from the station to the street and from the station to the railway network itself to create the multi-network, multimodal network model. And in order to incorporate other socio-economic data set or GIS data set, there's then use point of interest. It requires georeferencing and then also link it back to the network model itself. So after we run the spatial analysis on the network model, we will be able to verify or to compare those results with the socio-economic performance. So this is kind of the concept, the framework about the modeling. And to explain a little bit further on the details of the multimodal network model, here are the examples. So for A1, A2, A3, they are purely just the street network model, which we normally use in space impact studies. However, so the A1 is the one with the street network using metric distance. So as you can see, each grid is 1 kilometer by 1 kilometers. And then moving to the A2 scenario, now we convert the metric distance to the time cost, travel time distance. In this case, we convert it into the walking time distance. So just as a concept model here, the grid now turns into 15 minutes by 15 minutes, which is the cost for this modeling. And if we are looking at different transport mode, like in A3, if we look at the vehicular, if we are looking at the vehicular modeling, then the 15 minutes by 15 minutes walking distance turn it into just 5 minutes walking distance now. So although the metric distance is still the same, however, the travel time is different by different transport mode. So that's the A1 and that's the differences between A1, A2, and A3. And that's for A3, because it is considering the vehicular mode. So different types of the road will be assigned different travel time costs. For example, motorway, the car will travel faster on the motorway than the local street. So the travel time on those motorways will be even faster. For example, the 5 minutes by 5 minutes grid will turn into just 1 minute instead of 5 minutes. Then moving to the B1 scenario, which is the multi-modal network model. So the yellow lines here representing the railway network. But at the beginning, when we combine them all together, they are just purely the metric distance cost. If we would like to assign the different travel time to the model, then, for example, the B2 one is the combination of the pedestrian walking speed with the railway speed. So on the street level, the speed is still assigned by the walking speed. However, when you traveling within the railway network, the speed will depend on the speed of the train. So, for example, this one B2, the street network is still as a 15 minutes by 15 minutes grid, but the rail network will traveling faster with less time cost because the train speed is much faster than the walking speed. And the B3 is considering the combination between vehicular and the railway model. So this is different combination for the multimodal network model. So in space syntax methodology, we have the graph distance when running the spatial analysis, which is allow us to run the shortest path. Most of the study now identify that the most effective methodology is to use angular distance. So the first one is the angular distance. It takes the angular turn into account when navigating within the model. The second one is considering the metric distance. So like 50 meters, 100 meters away from the original points. So this is the metric distance cost. The topological distance cost is only considering the step from one segment to another segment, and then how many steps away from the original to the destination. Lastly, the travel time distance I apply here is taking into account for the travel time which will require to traverse that specific segment. So for example, the first segment requires 5 minutes walking, and the second one requires 5 minutes walking. So it becomes 10 minutes walking from the original, and then so on and so on. So this is the graph distance. And we also, when we run in the spatial analysis in space syntax, we also need to give the radius constraint. So, for example, in the A1, which is the conventional space syntax methodology, we use the metric distance as a radius constraint. For example, if we run integration 2,000 meters, and then that will mean the integration running with angular segment analysis with 2,000 meters in metric distance radius constraint. So it only considers every point of the shortest path within 2,000 meters from every point to every point. That's the radius constraint here. So different model type, for example, the B2, the multimodal network model, is a combination of the pedestrian movement plus the rail network. So this radius constraint will convert it into the travel time distance. To build up to develop the model for this research, it begins from the data acquisition. So we have 3 types of the data set. The first type is the network model itself. The network model itself is just like what I introduced previously. We have the street network, and then we have the railway network. And we also have the land use data set. And then later we have performance data set, including like census data, station usage, traffic data, economic data. This kind of data is to help us to identify or to verify how our spatial analysis working with those spatial influence or socio-economic impact. And so to clean up and to combine this modeling between the road network and the railway network, and it will create the multimodal network model. And others data set is just to georeferencing, classifying them, and then to combine them all together to become an integrated urban model. So we have a spatial model, which is a network model, which can allow us to run spatial analysis. And then we have the land use data set, we have census data set or other performance data set. We can join them all together to become the IUN, and then to allow us to do further statistical analysis to compare with our spatial network analysis. This is the idea and then the detailed framework here. I won't go too deep here. Yeah, so this research combining two case studies, and then the data set is quite essential for this two case study as well. In London, we are, because I'm based in London, and then I'm more familiar with all types of the data set. And so in London, we can access most of the data set from Ordnance Survey, which provide us a really high resolution for not only the network modeling, but also for land use or other performance data set. And those data sets are quite easy, accessible, and then free to use for research. However, in Taipei, the data set is more limited. We have to rely on OpenStreetMap for most of the data set. So one of the aim for this research is to show not only the high resolution research modeling could reveal the result, but also with the lower resolution, like OpenStreetMap network data set could also work in this way. Sorry, I think I jumped too fast. So with the combination with different model types, we have the street network, we have the multimodal network. We start to compare it with the annual average daily flow for the car traffic in London. And then we can see that in street network model, running with the vehicular travel time distance cost, the results showing high correlation with the metric distance graph analysis. So this is what we expect that because this is the car traffic data set. So if we use the vehicular travel time distance, it might work with the street network model. Another thing to highlight here is when the multimodal network model applied with the vehicular travel time, the angular graph distance pick up here instead of other graph measures. But generally speaking, the travel time distance is generally good to predict the car traffic with the street network model itself. So this is the graph. I mean, this is the image for the graph analysis for the street network model, which is running the vehicular travel time within 30 minutes as a choice model. And this is also rounding with the topological analysis. So both of the image pick up different results. For the first one, this one is the metric distance. So it's purely rounding with vehicular travel time distance. And then you can see how cars reach out or use most of the major roads as a high through movement area. And then for the topological one, you can see it also pick up most of the motorways and then the major roads. So the next test is to test the rail network in London. Starting from the strict network model, running with traditional conventional space syntax methodology. And then the second scenario is to consider the TFL services, including underground, overground, and DLR. And the next one is to combine also the national rail services into account and to consider the full railway network in Greater London. So these three types of model running with the traditional space syntax methodology with angular segment analysis, with metric distance radius constraint. The result is this one you are looking at is the result compared with the TFL multimodal network model with the strict network model. As you can see, some of the area intensify the integration result, but not the south. The south is not affected much by introducing the TFL services. And then the next slide, by incorporating those national rail network into the whole network model, the south of the London pickup intensify by the integration. So this could means that with those railway network, especially the national railway network, could help to intensify the whole centrality in this Greater London area, and especially for the south of the London. And this is also a graph to compare the strict network model with the multimodal network model. This is using the integration 1200 meters and using the angular segment analysis with the travel time distance. As you can see, the result is quite limited to those local area. The higher the warmer the color you see is the higher the increase in the percentage of the integration here. So those influences are quite limited to the local or neighborhood area. And when we move to a higher radius in 5K, we can see some of the area is into a intensify into as a regional connection. Lastly, in the 10K radius, most of the south area is integrated into the whole system, the network system. The choice measures is showing different. Most of the foreground network still remain the same without much of the increase, but most of the background network got the boost from the railway network. So this is a result of the choice 10K, which we can see. This is showing some different patterns than integration. And then the next is to compare those results with the station usage. The station, there's a 723 station taken into account in the Greater London model. And in this correlation, you can see the multi-modal network model correlate better with the station usage than the traditional street network model, especially when we consider the railway travel time distance, both in angular or metric distance or topological distance. This is another correlation showing that none of the choice result performing well with the station usage. Only the model with the multi-modal network model with the railway travel time distance radius constraint, and then with the angular segment analysis, graph analysis, has a better result. The next is to verify those numbers around the station with the travel to work by metro population. This is taken from the census 2011 output areas. So there's not like significant differences between the integration result and the travel to work TTW between these two models, the street network model and multimodal network model. But in the choice results, the MNM is outperformance with by the street network model. And the next is to test the result with the land use. Instead of the density here, I use the integrated urban model to create the land use accessibility. So the land use accessibility is to see how much, for example, in this case, how many retails you can reach within 50 minutes walking distance instead of the density or the pure counts for each area. So this is the image just to showing that those station usage and then those stations are somehow correlate with the retail accessibility and the services accessibility in the graph. And then we look at those results with within the station catchment. So I tested two scenarios, and actually I tested more than that. But these are two results which I think is more significant. So comparing the station catchment within 400 and 800 meters, the result showing that 800 meters catchment has a better result for both integration and choice with those land use accessibility. Then the land use accessibility of the retail and then the services also compare multiple various radii of the choice here. Then we can see lower radius like 400 or 800 meters performing a little bit better than the global scale radius. So this could indicate that those stations the railway network could influence the through movement within the station area more than the global scale. And so this is the scatter plot, and as you can see, some of the outliers are there because London in the central London is always a high usage of the station instead of but generally speaking, there's a kind of trend here. You can see comparing the choice result with the retail and services accessibility. So I combining the NNN choice 800 with the retail accessibility for those top 25%, and then put them into the graph. As you can see, this pattern is quite interesting. Those are quite aligned well with most of course, the central London, but there's some kind of linearity you can see following the railway network to the south and then also to the north area. This is just showing that the London plan for those highly intensified area, especially on the East London here. Some of them are quite aligned well with the station. So choice result with the travel to work by metro is also showing that high correlation with the multimodal network model with the rail travel time, and then no significant result with the street network dataset. And then I put all of them together to run a little bit of machine learning, and as you can see, we can reach around 67% of the prediction R-square when we consider choice 800 with other retail accessibility just to predict the travel to work by metro population. And now I'm going to compare and then apply what I have done in the London model, and then to apply it to the case study of Taipei. Just a little bit of background of the Taipei city. Taipei city is in the north of Taiwan, and the population in 2023 is about 2.5 million in the Taipei city, and 4 million in the new Taipei city, which is around the Taipei city as a greater Taipei area. So the total population is about 6.5 million. This is the graph just showing this is the CBD of the Taipei city, and this is the high intensified area of the new Taipei city, which is just next to the CBD divided by the river. And then this is a satellite image with the public transport network, the MRT system. There are 6 lines currently in Taipei with 117 stations. The network length is 132 kilometers in total. And then the daily commute is about 2 million in 2020, which means 1/3 or about 1/3 of the population in this area is traveling by the MRT. And this is just showing that most of the business or the office high intensified areas in the CBD. However, there are 4 million people which is living outside of the CBD, which is mostly on the west side of the river in this area. And those areas are only combined by the bridge, which is quite limited for the daily commute. So as you can see from the background, public transport network, especially the metro network, could potentially help this Greater Taipei area for the daily commute, and for people to traveling from outside of the CBD every day in between. So I use the same methodology to compare the street network model with the multimodal network model, and then to see what's the percentage increase of the integration in 10K radius. As you can see, of course, the CBD got enhanced by the public transport network, but also on the west side, the new Taipei city, there's a linear intensified by those the metro network in those area. And also notice that the north and the south area of the rural area of the Taipei city also got intensified by the metro services. And look at different measurements. This is the choice 5K radius result comparing the multimodal network model with the street network model. Interestingly, that the new Taipei city get most of the increase of the choice of the through movement. The grid system in the CBD get less intensified. So this is something a little bit different from London. And also, I use the business to consumer data set, B2C data set, to compare with the result. And this is just showing how those intensity of the business distribute around the city, and how they align well with the metro system network. So the B2C amount, I also put that into the correlation analysis, and then you can see integration 5K pick up a little bit, but nothing really significant or high correlation with choice. And also compare with the land use accessibility. Of course, the commercial land use accessibility is correlate well as expected with the business to consumer account. So comparing the result between London and Taipei, the percentage increase in integration 1200 with the after the implementation, London shows clustering around the stations. However, in Taipei on the right, there's a linear intensify along the MRT network. When we look at the integration 10K, it looks like London shows a greater increase in the connectivity, especially on the suburban area. However, in Taipei, some of the suburban area also intensify, but the CBD also get some intensify as well. When you look at the choice 5K result, as I mentioned before, the backbone network in London get increased. However, the foreground network still remain the same. Then in the case of Taipei, you can see most of the grid system in the CBD has less influence, but the rural area, which is on the west side of the river, got boosted. The multi-scale integration. So I combining both 1200 meters and 10 km radius integration, and showing those top 25%, and then those results are correlate well in the graph in the image. showing with the intensify of the station usage. Compare the case of London and Taipei. As you can see, the integration correlate well on the global scale for London. However, the Taipei is correlate well in the local scale. So this is showing something about how different about these two cities. And so in London, this might indicate that the railway network help to intensify the whole centrality for the whole network system. However, in Taipei, the MRT system are more intensify those local station neighborhood. As you can see here, a choice result are more significant than the integration around the station area in both cities. So lastly, I combining those measurements, the choice and the commercial accessibility for those top 25%, and then to plot them into the image, and then also comparing with the station usage. This graph shows that some of them are aligned pretty well in both cities. So in summary, the MMM incorporating with travel time distance can be integrated with the space syntax methodology and could potentially improve the analysis of our urban form and assess how this rail network influence the social-spatial outcomes. In the global scale, the MMN highlights those areas with the centrality increase by the railway services in the regional scale. And in the neighborhood scale, the result shows that the through movement patterns it could be generated by those railway services, especially within 800 meters station catchment. Lastly, the limitation and the future research recommendation from this study is that currently the angular segment analysis is still performing better, but when we combine with the travel time distance radius constraint, it will be able to effectively predict some of the commuting or business patterns, especially around the station area. For the future study, we could think of a different way to isolate the graph analysis using different graph analysis. For example, using angular segment analysis in the street network, and then use the travel time distance cost in the railway network, and then running them all together at the same time. But this requires further test and then computational technology. So this is the presentation for today. I'm happy to answer any questions if you like.